Hello, my dears. This is module 2 of instrumentation and measurement. Today we are going to start the material of week 1, which titled as DC and AC bridge operation and application. Delivery plan of module 2 is having 3 parts. The first part will be covered in week 4, then the second part in week 5, and the last part will be covered in week 6. So we will start by DC bridge, where the DC bridge consists of 4 resistors and battery arranged in certain way to detect the nil condition of the current flowing between the terminal of the bridge. So between the terminal of the bridge, which we are going to see in the next slide, there will be a meter or galvanometer to measure the current flowing. Usually the DC bridges used to measure the value of resistance. So usually we have 4 arms, as I said. One of the arms is unknown. So we are using the DC bridge to measure the value of that arm, the value of the resistance or impedance in that arm. The types of DC bridge are Weston bridge and Kelvin bridge. These are the bridges which we are going to study here. This is the bridge I mentioned in the previous slide. But here we are starting with Weston bridge. In Weston bridge, we are having, as I mentioned earlier, the arrangement of 4 resistors connected between 4 arms. So this is R1 connected at arm A, C, and the resistor R2 connected at the arm A, D, and R3 connected between CB with R4 connected between D and B. Now the battery E is supplying them on the arrangement you can see here. Usually one of these resistors are unknown. Let us say R4 is unknown. So R1, R2, and R3 are known to us. So the bridge is used to calculate or to evaluate the value of R4. Usually Weston bridge used to measure the resistor starting from 1 ohm until few mega ohm. In the operation of Weston bridge, we are depending on a balance condition. What is the balance condition? Balance condition will be when the voltage at the point V1 or the voltage V1 at point C with the voltage at point D, V2, when they are equal. So if the two voltages are equal, we are going to get the current flowing between them through the galvanometer equal to 0. That means Ig equal to 0. So this is a way, or we put the galvanometer to detect the balance point. The balance point will be when the current Ig equal to 0. Now, the condition of balance will be, as I said, when VCA equal to VDA. VCA, when this voltage equal to this voltage, we are going to say that the condition is balanced. Why do I need to get this balance? What is important of balance condition? Because we are going to measure unknown resistance, as I said just now. So if R4 is unknown, we are going to connect it between the points D and B, and then we are going to look for the balance condition. So we will adjust R3 until the current flowing in Ig equal to 0, until the current of the galvanometer equal to 0. Once the current in the galvanometer equal to 0, there is a formula we can apply it to get the value of R4. So the formula will be developed in the next slide. So here we will develop the equation which we will be able to use it when the condition is balanced. So remember, I said the condition is balanced. That means we have to make sure that the situation or the bridge is balanced. Then we will apply the formula. That's why I am going to start with the assumption of balance condition. So I'm going to say that V1 equal to V2. Now, how am I going to calculate the equation? How am I going to get the equation? We are going to depend on voltage divider rule. If you look at the battery E, look at it carefully, you are going to find that the battery is supplying the resistance R1 and R3. So the voltage E is applied to R1 and R3. And in the same time, if you look at E, also it's applied to R2 and R4. That's because this branch paralleled with this branch. So the voltage on them is the same. That's why when I want to start the evaluation, I can apply voltage divider rule to either side. So we are going to apply to both, but let us start with the first side where I want to calculate the voltage between C and A. To calculate the voltage between C and A, we will call it V1. So V1 is equal to R1 over the total resistance in series, means R1 plus R3, all multiplied into E. That's what I'm showing here. So this is equation number 2. Same thing we can use to get the voltage divider rule on R2, the voltage drop on R2, which we will call it V2. So you are going to get this equation. So if I'm having, as I assumed earlier, if I am having V1 equal to V2 as shown here, that means this value equal to this value, which means this value equal to this value. I'm going to get this equation. Let us see what will happen after this. Okay, here if I simplify the equation shown earlier, simplify it by cross multiplying its side, you are going to end up with R1 into R4 equal to R2 into R3. And this situation will be only when the bridge is balanced. Now keep in your mind that I am looking for the value of R4. So if I want to calculate R4, I can rearrange the equation to get the value of R4. Now R3 is a resistor, which a variable resistor to be adjusted until I get balance. For that, I need R3 to be a resistor which I can adjust it, and by the end I will know its value. When I adjust it, I know its value. R1 and R2, they are having a ratio. That ratio is fixed for any bridge, meaning when you get the bridge, you know the ratio between R2 to R1. Okay, we will look at this example to calculate the missed value of the resistors. He's saying here a Weston bridge has the following arms: R2 equal to 1.47 kilo ohm, R3 is equal to 2 kilo ohm, and R1 equal to 500 ohm. So the three values are known. What is the value of unknown resistor R4 bring the bridge to a null condition? Again, null condition means balance. Null condition means the current in the galvanometer is equal to 0. So he's saying here, what is the value of R4 which make the current here equal to 0? That means the bridge will be balanced, which means I can use this formula. So in this case, we can apply the formula by saying R4 equal to R2, R3 over R1. Substitute the values, and you are going to get the value of R4 equal to 5.88 kilo ohm. That means if you put this resistor here, you are going to get the value of the current equal to 0. What is the reason behind this calculation? Is getting the value of R4. Another example here, a Weston bridge has a ratio of 1 to 100. 1 over 100. That means R2 to R1 equal to 1 over 100. So what is the value of R2? We don't know. The value of R1 we don't know. We know only the value between the ratio of them, or their ratio. At the first balance, R3 adjusted to 1000.3 ohm. At first balance means we are putting the bridge, we are connecting the bridge, and we are going to adjust R3. I will adjust R3. R3 is variable, as you see. It's a variable resistor. So we adjust it until we get the current here 0. When I get the current here 0, I found that R3 equal to 1000.3 ohm. Then that's for certain value of Rx. I don't know what is the Rx. So forget about Rx right now. We are just trying to understand what he means here. So I put Rx, I adjust, I got the value of the current here equal to 0 when the resistor R3 equal to 1000.3. Now, then the value of Rx is changed or then changed by a temperature change, because Rx can be a temperature sensor. Sometimes as we mentioned earlier, we will find that the output of a sensor is a resistor. So if the output of heat sensor is a resistor, what does it mean? It means when the heat increase or when the heat change, the resistor will change. So here he's saying that the resistor Rx is changing due to the heat. So what will happen if Rx change? Once it's changed, the bridge will lose its balance. That means we will get current flowing in Ig. So he's saying Rx change by the temperature change. Now the new value for R3 to achieve the balance condition again is 1002.1. That means when we get this resistance change, the current will start flowing to the galvanometer. So we are going to get a current flowing in the galvanometer. How to stop the current flowing in the galvanometer? By getting the balance. How to get the balance? By adjusting R3 again. So I adjust R3 again to find that the current stopped flowing in the galvanometer when the resistor of R3 equal to 1002.1 ampere. Now the question is, find the change in Rx due to the temperature change. So he wants to know what is the change in Rx. Very simple, we can calculate Rx at the first condition, and then we calculate Rx in the second condition and find the difference between them. As you see here, at first balance, when it's balanced at the beginning, so R3 equal to this much. See how we put the equation? We put the equation as R3 into R1 over into R2 over R1, so that we can use this as a ratio. It's the same thing anyway, nothing changed here. So we will find at the first balance condition, Rx, the unknown resistor, is equal to 1000.3 into the ratio. So I got it 10.003. Now in the second balance means when we change R3 until we get the balance again, we are going to put the new value for R3 and calculate. Same thing. So we are going to get the resistance Rx equal to 10.02. He doesn't want Rx. He doesn't want neither Rx at the first balance nor at the second balance. He wants the change in the resistance. The change in the resistance. So we find here that the change in the resistance is the difference between the two values, which equal to 0.018. So that's how we can get the change of resistance in such a case. Somebody will ask, why do I need to get the difference or the delta R? Why delta R is needed? Because sometimes what is calculated in terms of temperature, we are not calculating the temperature, or the table given to us is not giving us the temperature for each resistance. No, it gave us the change in temperature. That's why here I'm calculating the change of resistance, which will tell me the change of temperature in the table of sensor. Another kind of DC bridge is Kelvin bridge. Kelvin bridge and Weston bridge are the same actually. Kelvin bridge is just a modification of the bridge of Weston. If you notice, I mentioned earlier that Weston bridge can measure the resistance starting from 1 ohm up to few megas. How about if the resistor which I need to measure less than 1 ohm? You remember that we are dealing with instrumentation. Instrumentation means the things are sensitive. I mean, we are very much concerned over small values, the small changes. That's why sometimes I need to calculate the small resistance or small change in the resistance. So if the resistance less than 1 ohm, how can I measure it? Actually, the difficulty will come here when I want to measure a resistance which lower than 1 ohm. Why measuring less than 1 ohm is difficult? Because the wires which used to measure the resistance, the wires used to measure the resistance, they themselves have resistance. So the resistance of wire will make error in the measured resistors. measured value. What I mean here, if I'm having resistor here, let's say I'm using the simple way, and I want to measure it by ohm meter, for example, this is ohm meter. There must be a wires here to measure the resistance. So the wire are going to be connected to the terminal of resistor. This is the wire, and this is the other wire. Now, the ohm meter here is not measuring the resistance of this resistor only. It's measuring the resistance of this resistor plus the resistance of the wires. That means the value I am measuring having error. Now, if I am measuring a resistance of 1 mega ohm or 1 kilo ohm or even 100 ohm, the resistor of wires are very small compared to them, so we will have no problem. But if I want to measure a resistance which equal to, for example, 0.01 ohm, the resistance of the wire will affect it. That's why Weston bridge will not help us here. So Kelvin bridge made for that purpose, for that reason, just to eliminate the effect of wire in measuring the resistance. Notice here, Kelvin bridge is very similar to Weston bridge. We are having 4 resistors, R1, R2, R3, and R4. And we have a galvanometer to measure the balance. What is the difference here? To eliminate the effect of the wires, the wire of the galvanometer. To eliminate this, we are going to connect the galvanometer not at fixed point. We are going to put the galvanometer at known point to us. What is the meaning of this? Let us consider the connector between Rx and R3. I'm talking about this connector. When I'm connecting the terminal of the galvanometer to that point, I'm not going to connect it randomly. Here, all wires, keep in your mind, all these elements are wires. We are not going to connect it randomly. We are going to connect it at certain ratio between the two terminals. This is resistor, this resistor, this resistor. The connector between them, we will keep certain ratio in the connection. So I'm not going to put this terminal randomly. I will put it at specific value. Remember now that when I want to consider the resistor RNP, RNP, this resistor, it's going to be added to R3, and RNP going to be added to Rx. That's how I'm going to take the wire, the resistance of wire added to the resistors in the bridge. So in this case, I'm going to get the effect of wires or the resistors of wires added to the balance condition, so they are not going to cause a problem in that. But for this point, I have to put the resistor at certain point, the terminal of the galvanometer to be placed at certain point. Here he's telling us about the random connection of the galvanometer wire, this one. So he's saying if you connect the galvanometer to point M, that means here, when I say point M, means, let me just erase this, means the connector will be something like this. This is the connection only, this one, and that's how. Forget about this wire, forget about this wire. So that's how the connection going to be. In this case, you are going to find that the resistor between M and N, that means this resistor, this part, and this part, which let me say it's all this element, all this part, as we agreed earlier, it's having resistance. It's going to be added to Rx, which is going to make the measured value of Rx not only Rx, it's Rx plus this resistance. That's one thing. What about the other way around? If I make it connected to the other side, I mean if I connect the terminal to point M to point N, the circuit going to look like this. So in this case, the resistor which I'm talking about this resistor again here, this one, this wire actually, the resistance of this wire will be added to R3. It means it's going to make the balance is not very clear. That's why we are not going to put the terminal of the galvanometer neither at point M nor at point N, then where am I going to put it? I'm going to put it with keeping in mind that certain ratio between M and N must be satisfied. We will see this in the next slide. So now how am I going to connect the point or the terminal of the galvanometer? As you see here, he's saying you are going to put the terminal of the galvanometer at point P. What's special in point P? We are going to look for point P while doing the measurement. We will make it such that the terminal or the distance or the resistance, let us say, between or at NP, that means this one, over RMP, this one, is equal to R1 over R2. So we will make it like this. This one, this resistance over this resistance is equal to this resistance over this resistance. So that's how we are going to get the reading correctly. Now, if the situation is like this, this is the ratio of the connector, the ratio of the connector to the ratio of the resistors. We keep this one in our mind as equation number 1. Now, at balance condition, we are going to find that R2 into Rx plus RMP equal to R1 into R3 plus RMP. Remember that this is just same to the previous equation, same as the previous equation, except here we don't have Rx by itself, it's Rx with this part. Here we are having R3 with this part, which will be similar to the previous balance condition in Wheatstone bridge. Now, if I substitute equation number 1 into 2, I'm going to get to this situation. By simplifying the equation, we are going to get to this condition. Notice that this equation is similar to the Wheatstone bridge. The condition we are getting here is very similar to Wheatstone bridge. When can I use this formula in Kelvin bridge? When can I use this formula in Kelvin bridge? Is it same as Wheatstone bridge? Let us see. I think in our discussion, we came to the point to say that Kelvin or this formula can be used in Kelvin bridge after satisfying two conditions, not one condition like Kelvin bridge. The first condition, this current supposed to be 0, and the connector of the terminal of the galvanometer must satisfy this condition. If you do these conditions, or if you obtain these conditions, that means you can apply this formula to calculate the value of resistor which less than 1 ohm.